In this video, we're going to learn something called synthetic substitution and synthetic division. We'll know what it is, how to do it, and what it finds for you. We'll also see how synthetic division relates to synthetic substitution, and we'll talk about the remainder theorem. These topics all relate to content from sections 3.4 and 3.5. This first slide asks us to find f of 3 and f of negative 1. It might be important to recall that when something says they want f parenthesis a number, that doesn't mean f times 3. It means the function will be f, as we have right here, and 3 will be in place or substituted for an x value. So in this case, for the first one, we want f of 3. That means we want 3 to go in place where all the x's would have been in the original equation. So I've substituted those in. You could use a calculator, you could use Desmos, just use some mental math. If we did that, we would find that when you plug 3 in, it will equal negative 16. Now if we go look at the graph, let's see if we know they're correct. That means this function is graphed here in green, and if we plug in 3, if we look at this graph, if we had Desmos open, we could click there and get it exactly, but that actually is the coordinate 3, negative 16. So by plugging an x value into a function where x is used to be, you get the y value. So quickly here, if we want f of negative 1, that would mean we put negative 1 in for all those x locations. And when we do that, we actually get 0, which is even easier to see on this graph here because at negative 1, our y value is 0. And that's kind of important because we've been working with x-intercepts and factoring to find those. So we're going to use that to continue. Now, plugging in 3 or negative 1 to the function may seem a little daunting to you, especially because you can make little simple errors, or if you don't have Desmos or a calculator, minor math errors can be an issue. So there's a cool shortcut called synthetic substitution, and here's how it works. If you were going to plug in 3 into a function, let's say you wanted to plug it in up here for all the x values, but you'd rather do something different than doing all that math. You're going to put a 3 in a little box here. We'll set up our synthetic substitution like this all the time. You're going to put that 3 that you wanted to plug in into this little box. Now, you're going to write out all of the coefficients of your polynomial. That means I had 1x cubed, so I put a 1 down. I had negative 4x squared, so I put a negative 4 down. Negative 3x, so I put a negative 3, and a plus 2, so I put a plus 2. You can't just write it however you'd like. To keep the process working, you have to have it in standard form first, and then write all of the numbers or coefficients out in descending power order. Notice how I don't have any of the x's included. We just do the coefficients or numbers. And this was the third power of x, the second power, the first power, no power. We can talk more about it later, but if you ever would be skipping a power, say there was no x squared, you'd have to put a 0 in to accommodate for that. So how this process goes, you're going to drop the 1 down below this line. And so if I put a 1 there, we just simply, our first step is to drop that 1. Then we're going to take our 1 and multiply it by this number in the box. So 1 times 3 is 3. And we throw that product or answer of 3 out here. So then our step with these two numbers stacked, we're going to take our negative 4 and add it to 3. And that would give me negative 1. So with negative 1 here, again, that was from negative 4 plus 3, I'm going to multiply that negative 1, repeat the process, multiply it by 3, which is now a negative 3, and throw that down over here. Same thing, I'm now going to repeat the process here. We're going to add negative 3 plus 3, or negative 3 makes a negative 6. And then I'm going to multiply that negative 6 by 3. Okay, so I use my orange here to keep it the same. If I have negative 6 times 3, I get negative 18, and I'm going to throw that number over here. So I have negative 18. And negative 18, I'm going to add that to the 2, just like I did the last one. So negative 18 plus 2 makes negative 16. And that number should look familiar. If you recall on the last slide, when we plugged in x equals 3, we got our answer to be negative 16. Now when we did this synthetic substitution process, we had our negative 3 in the box, we wrote our coefficients for the cubic that we had, and our final answer here was the y value for when we had an x value of 3. So synthetic substitution works to find you the y value of a function at any given x value. Let's try it real quick here with our negative 1 and see if it also matches. If I put my negative 1 in here in the box, I'm going to write all the same numbers because I'm dealing with the same polynomial. Put them in descending power order. I drop down my first term of 1. Then I'm going to multiply that by the number in the box up here. So 1 times negative 1 makes negative 1, and we throw it down there. Then I'm going to add these together. So negative 4 and negative 1 make negative 5. I'm going to multiply negative 5, color changing issues here, negative 5 times negative 1 makes positive 5. Then if I add these together, a negative 3 plus 5 makes a 2. I'm going to multiply 2 times negative 1, and I get negative 2. And when I add these together, I get 0, which if you recall on the last slide when we plugged in negative 1, we actually got 0 for our y value. It's because it was the x-intercept. So synthetic substitution can help you find y values when you know an x value with this crazy process here without having to actually plug it in and do all the cubing and the squaring and the combining carefully. Now because we know one of these was an x-intercept, not only from our plugging it in, but looking at the graph, remember back when we were working in a previous section, this little example, this is a different example here. When you had negative 2 as an x-intercept, x plus 2 was a factor. Same thing here when x equals 1 was a 0, x minus 1 was a factor. So it's going to ask you from your work here above, what was one of the zeros? Well, we know one of the zeros was at, when you plugged in negative 1, you got 0. So my 0, we would say, is at x equals negative 1. That means my factor is x plus 1. So how does that help us? So here we have the same information. When our x-intercept is negative 1, our factor is at x plus 1. Well, in a previous section, we were looking at how you might be able to graph polynomials without Desmos. We wanted to be able to factor something like this. We're not so great at factoring things with cubics. But by realizing that negative 1 was a 0 and x plus 1 is a factor, that means it's going to look something like x plus 1 is one of the factors, and then there's going to be another multiplied polynomial out here that would get us back to this standard form. So we kind of found one of the pieces, if you will, for the factors. Let's use our box method real quick, an area model. If I had an x plus 1 as definitely one of the things to multiply something else by, I don't know what it would be, but I want to figure out what it is, to get this x cubed minus 4x squared minus 3x plus 2. Let's try to do some guessing here in our box. I know that I'm going to have an x cubed. So if x is here, this is going to have to be an x squared. So eventually I can get my x cubed in this box. I find these somewhat to be like a Sudoku math problem, so you may find them fun as well. Let's talk about this final term down here. We know that we want 1 times something to be 2. That's because this final term here is just a constant. There can't be any x's with it. So we know that this term right here on the end of this trinomial we're looking for is going to be a 2 because 2 times 1 makes 2. Now that also helps me fill out some middle boxes here. Like this is going to be 2x because 2 times x is 2x. And this one's going to be x squared because 1 times x squared is x squared. We now just need to figure out what our middle number is for this trinomial. We need to remember that we have to get a negative 4x squared. And currently with our setup, we have a 1x squared. So I'm going to need negative 5x squareds in here to get negative 4. When I combine these, that means I'm going to need a negative 5 out here with an x because negative 5x times x makes negative 5x squared. Now let's hope this finishes where if I wanted to get negative 3x, I know negative 5x times 1 makes negative 5x, and good news, negative 5x plus 2x makes negative 3x. So what does that mean? We have just found the second factor or polynomial besides the x plus 1 that should go here. So x squared minus 5x plus 2. And technically that's what they wanted here. So we have just found the binomial times the trinomial that would make that cubic. But if you don't prefer to play the little box method game where you're filling in the pieces to try to factor it, and again, remember we're trying to factor because if you can factor any polynomial down to very linear terms like x plus 1 and x plus 2 and x minus 3, you'll know the zeros and you can sketch it, and that's our goal for you. But again, if you didn't like filling in all of this box here and guessing these and getting our final answer of x squared minus 5x plus 2, think of our previous work. When we plugged in negative 1, we got 0. We used this synthetic substitution to get an x to match a y. Look at your coefficients before your 0 compared to the one you got when you made your final factor there with your trinomial. They match. That means not only is synthetic substitution, that little fun process where you drop down the 1 and multiply and add, a way to find an x that goes with a y, it's also going to be a way to find what polynomial is left over that would give you the other factor. So keeping with this problem, we have our x plus 1, we have our new factor we found from the box, or we realized it came from synthetic division. To find the other zeros, we know this first 0 at negative 1 comes from that first factor. But this one, the zeros of this, we have to use the quadratic formula. Now, you could always try to factor this little red underline to the quadratic that you have, but it's not going to because nothing multiplies to 2 but adds to negative 5. So in magic form here, I've done the quadratic formula, got my a, b, and c, and I've come down to find my two roots. They're still real. Notice they didn't have a square root of a negative. 4.56, and that seems to be matching here. Looks pretty good for that kind of 0. And 0.44, and there we have that other. So for this example, it comes from 3-5, and we want to find this, use this graph to find one of the zeros of this polynomial. Well, I see it crosses at 2, so my x equals 2 is a 0. That means one of my factors is x minus 2. But I want to find the rest of the equation. So instead of using that guess and check, I'm going to put my 2 in here, because that's my 0, drop down my 1, multiply by 2, put that answer here. Add 2 plus 1 gives me 3, multiply by 2 gives me 6. Negative 3 plus 6 is 3, multiply by 2 gives me 6, and add those together gives me 0. Now remember, each of these numbers here in the top row all came from the coefficients of my regular polynomial. So that means x minus 2 is the first factor, and each of these new numbers, 1x, it'll be now 1x squared, plus 3x, plus 3. So these numbers now represent the new polynomial numbers to finish out my factor. It's important to remember that since we started with a cubic, we knew one of our factors, and this was a power of 1, we knew this next one when we got these numbers was going to have an x squared. We're going to now use this red x squared polynomial. If it factored, we could find more zeros, but it doesn't. So it's time to use the quadratic formula. So in power math fashion, here is the quadratic formula when our a was 1, our b was 3, and our c was 3. Here are my final solutions. Note that the square root, the discriminant, if you will, was negative. That meant we had imaginary roots. Well, that should make sense here because this graph never actually comes up to touch the x-axis again. But we do know that if it's degree 3, we have to have 3 zeros. And our 3 zeros are x equals 2, x equals this, and x equals this. Here's a couple theorems you can look at. Basically, we have our number we plugged into an equation. If you plug it in and you get an answer of 0 to a function, that meant x minus that number was a factor. Look at that first part we did of this video. Also for the factor theorem, again, if you get an answer of 0, then x minus a is a factor when you do that synthetic division. Getting no remainder means x minus a is a factor. Here are some examples in the packets that can help you practice synthetic division, and that helps us find the zeros. That's why we need synthetic division.